Good morning, everyone. Happy Monday. So I know that I said I was going to post these notes over the weekend and I didn't. I am sorry. I apologize. I'm going to post them now, though, and then you guys should have them copied into your notebooks by Tuesday. Okay, so these notes are on natural logarithms, and in order to understand what a natural logarithm is, you have to first understand what the number e is. So yes, this is an E right there in the title of the notes. Okay, so what is E? Well, E is pretty much it's just a number, but it is an irrational number. With an approximate value of 2.71828. And so on and so forth. So it's just an irrational number. Kind of think back to the irrational number pi. So you all know what pi is. Pi is approximately 3.14. Well, E is another type of irrational number, and it's approximated at 2.1828. Okay, so it's going to look a little funny because you've obviously never seen it before, but just think back to it. E is just a number. It's a number. And the reason why we have it is because E often occurs as the base of exponential functions and logarithmic functions that describe real-world scenarios. So like in this class, we're not going to really dive too much into those real world scenarios. But next year in calculus and if you take more advanced math or science courses, you'll probably see this number E in those real world scenarios. Okay, so E, when I'm talking about the number E, it's just an irrational number with an approximate value of 2.71828, and it goes on forever. Okay, so with E, you can have exponential functions. So exponential functions with base E are what we're going to call natural base exponential functions. And that will pretty much just look like something like this. F of x is equal to e to the x. And again, that probably looks weird, but just think about it. Like we've had exponential functions that look like f of x is equal to 3 to the power of x, and that doesn't look weird to you. Your base is 3, and then you have an exponent, a variable of x in the exponent. This is the same exact thing. It's just that your base is e, which again, it's just approximately 2.7, and so on and so forth. Okay. Now you can have base E exponential functions, and you can also have base E logarithmic functions. Now this is where this idea of a natural log comes in. So logarithmic functions with base E are what we call natural. Oh no, here we go again. Same thing that happens as always. Okay, there we go. These are what we call natural logarithms. So, what are these? An example of this is f of x is equal to log base e of x. So, in this case, we have a log. My base is e, and which is why we call it a natural log. These are base e logarithmic equations or functions. However, honestly, we never really ever write it like this. If you have a log of base e, this is often then abbreviated as the f of x is equal to the natural log of x. Okay, and yes, I know that this probably looks a little funny. This is actually the letter L, this is the letter N, and I know you're like, well, it's called a natural log. Why do we not put it as NL rather than LN, like I almost did right now as I was writing it? I don't know. I have no idea why they didn't do that, why they didn't keep the order of the letters NL. They flipped them, but that's just the way that it is. You've probably seen this LN button on your calculator before, just like you guys had probably seen the log button before on your calculators, and you probably never knew what they were, but now you know. So pretty much if you have a log of base E, rather than writing it as log base E, we just write it as the natural log of x. Okay, and you say it that way. You say the natural log of x. Okay, so what we're going to be doing today is pretty much what we've been doing before, but you're only going to be working with functions that have a base of e. So they're all natural log functions. And all of the properties from logarithms still carry over. So let's convert between forms. So you've done this before, but you've only done it with numbers. Like you've done this before with 2 to the x is equal to 24. And I know that you all know how to convert this into log form. However, just rather than having a base of 2, you're going to have a base of e. So in order to convert this one into logarithmic form, what you're going to go ahead and do is you're going to write the word. And just for like showing purposes, I'm going to write this out for you. But typically, again, you could skip this step if you wanted to. You can put this as log base e of 24 is equal to x, right? You guys have done this. But what did I just tell you? Rather than writing right here log base, oops, I did not mean to erase that. I meant to highlight it. Rather than writing log base e, we can substitute it with just the natural log. So here, this would just be the natural log of 24 is equal to x. And I have converted this into logarithmic form. Okay. I have faith that you guys can do the rest of those. Now, you can also convert these equations from natural log form into exponential form. In order to do that, you just have to imagine here, this natural log, even though we do not see a base written with this natural log, remember, this has a base of e. There's like an imaginary e there. So to convert this into exponential form, it would be this base raised to this exponent is equal to this. So this would be e to the 58 is equal to x. And I have now converted that into exponential form, okay? So the same rules apply with the natural logs as we've already covered from regular logarithms, okay? So that's converted between forms. We can also simplify natural logs. Again, it's the same properties. You can both condense and expand them. Let's go ahead and do number 8. Let's condense this expression into a single logarithm. And again, even though it's telling you to condense it into a single logarithm, because you know you're working with the natural log, you're actually going to condense this into a single natural log. Again, same rules apply. So we have a natural log with the base of e of 63 minus 2 times the natural log of 3. Both sides have a common base here, so you can go ahead and use your rules to simplify this out. This coefficient, you can take this and apply it to the 3, so this will be the natural log of 63 minus the natural log of 3 squared. 3 squared, as we all know, is 9, so this would be the natural log of 63 minus the natural log of 9. Now you have 2 logs, they have the same base, they're being subtracted. So to condense this down, you would take the 63 and divide it by 9. So this would be equivalent to the natural log of 63 divided by 9 is 7. And again, I know it looks funny, I know it looks weird. You're probably like, that looks like the word miss in 7. It's not, it's the natural log of 7. All right, we can also expand these out. So just like you saw me condense them, we can expand them. Again, you've done this. It's just that now you're working with a natural log rather than a logarithm with another base. So, for example, like number 12, let's do number 12. Let's expand this one out. I know a lot of you guys were saying that you struggled with expanding, so let me show you how you guys can rewrite these to simplify them out. So we obviously know that, I've told you guys this before, the square root of x is the same thing as x to the 1/2 power. The cube root of x is the same thing as x to the 1/3 power. So I can rewrite this that you see here as the cube root of n squared, n as the natural log of m squared n all raised to the power of 1/3, right? I've just converted it from a cube root to the 1/3 power. And then here you want to expand this out. So you can separate, first of all, you can take this exponent right here and drop it up to the front and add it as a coefficient. So this will be 1/3 the natural log of m squared n. And then right here between the m squared and the n, they are being multiplied together, so you can expand it as two separate logarithms as the sum of the natural logs. So this will be 1/3 natural log of m squared plus 1/3 natural log of n. All right, I have split this up as the sum of two logs. And then from here, you just need to simplify down this exponent. You know that you can take this exponent and drop it down to the front. There's obviously already a 1/3 there, so you're gonna take that. I don't have much space, so I'm gonna have to write off to the side, but hopefully you all have space. This will be 2 times 1/3, and then natural log of m plus 1/3 natural log of n. And then here, what's 2 times 1/3? You just put this over 1. This will be 2/3 natural log of m plus 1/3 natural log of n. All right, and then I have taken the original expression and have expanded it out. Again, not anything that you haven't done before. It's just now you're working with the natural log. Okay, so this should hopefully be a refresher of actually condensing and expanding and rewriting and converting between forms that we've done before. You're just doing it with a new type of function, the natural log function. So let's do the back ones. These are also things that you need to know how to do with natural logs, just solving them. Again, you've done this. Making sure that we check for extraneous solutions as well, because remember, you cannot have a negative, you cannot take the log of a negative number. So on this back side, maybe I can go ahead and do like 2 questions, and then you'll be expected to do the rest when we have time in class time on Tuesday. So for example, let's do number 15. So right here, we're going to go ahead and simplify, condense down the left side first. This will be the natural log of 72 divided by 4. Why did I do division? Because these two logs are being subtracted. So what is 72 divided by 4? Well, that would be the natural log of 18 is set equal. Over here, on the other side, I have addition, so I can condense this as the natural log of, I would take 6 times a minus 2. Make sure that you distribute out this 6 to everything inside the parentheses. So this will be the natural log of 6a minus 12. And then now I have 2 logarithmic expressions on different sides of the equal sign. They have the same base, so I can use the 1-to-1 property to just set 18 equal to 6a minus 12. You add 12 to both sides, so then you end up with 30 is equal to 6a. You divide both sides by 6, so you get a is equal to 5. Make sure that you check this answer before you say that it's a correct answer. You take this 5 and you substitute it in here. 5 minus 2, that would give you 3, so that works. And that's the only spot that I have to substitute in, so this is a good solution. Okay, I'll do one more, maybe some of here at the bottom, because remember, these are like the type 1 logarithmic equations that we did the other time, where you have a log set equal to a log, or in this case, a natural log set equal to a natural log. There's also the other types, whenever you have like these types without the natural log, where you're going to instead have to convert this into a natural log. So let's, for example, do number 20 here. Number 20, I want to go ahead and isolate this expression right here, the one with the variable. So I'm going to add 6 to both sides. So this would be e to the y plus 3 is equal to 30. Now, obviously, to solve this, is there a way to get a common base between e and 30? Well, definitely not, because e is like approximately 2.7, so obviously that is not going to be able to be represented as 30. So instead, in order to solve these, you're going to have to convert this into logarithmic form. But because my base is e, you're going to use the natural log. So this would be essentially log base e of 30 is equal to y plus 3. Remember, all I did here was convert this into logarithmic form. You all have done this. Now, what is the log of e? Well, again, that's just the natural log of 30 is equal to set y plus 3. So in order to solve this, you just evaluate on your calculator what is the natural log of 30. Since I don't have a calculator, I will go ahead and just use Desmos. So you can look through the functions or on the calculator, just press the natural log of 30, and you get approximately 3.4. So I can go over here and substitute in, rather than the natural log of 30, I know that that's approximately 3.4. Is that equal to y plus 3? Solve this for y by subtracting 3 to both sides. So you get y is approximately equal to 3.4 minus 3 will give you about 0.4. You do need to check it. If I were to substitute in 0.4 right here, this would be 0.4 plus 3, which is about 3.4. Obviously, you can take e to that exponent. It all works. So this is a true solution. All right, so this is what the natural log is. When you guys come on Tuesday, we will practice the rest of these questions in class. It's pretty much just understanding and getting down that whenever you have a log of a base e, that is what we call, that's a special type of function, which is, we refer to it as the natural log, and we abbreviate it as the ln. And then all the same properties of logarithms that we already know, like the ones that we've done in the past, like these, and the process of solving them still carries over. You're just now doing it with the natural log. All right, let me know if you have any questions.